Hello and welcome to the next lecture in our course Introduction to Data Analytics. In this lecture we're going to be talking about random variables and probability distributions, and this will be the first lecture of a series that cover this topic. Just to recap on what we have completed so far, we've finished looking at descriptive statistics and the use of various use of graphical and visualization techniques in descriptive statistics, as well as the use of summary statistics. Within summary statistics, we looked at measures of centrality and measures of dispersion. So jumping into this topic, the quick question is, why do we need to talk about probability distributions? What does it have to do with data? Is it just like a mathematical concept? What does it have to do with data? And the quick answer to that question is, if you go back to the use of the histogram, we express that as a way of describing data. Essentially, the histogram is, if you look at this picture on the slide, the histogram is those vertical grayish blue bars that you see on this graph. And that describes the data, that summarizes the data in some way. But you might be of the belief that if you redo this exercise, if you collect a new sample, you'll get bars that look slightly different. And the question is it really coming from a probability distribution? Is it coming from some other mathematical function that closely approximates this histogram that you're seeing? And that red line that you see in this is the attempt to fit this mathematical function. And the core idea here is that this data is being generated by this probability distribution function, which is that red line, and the histogram is what you see in terms of data, because not every time are you going to get data that looks exactly like the red line. So it's in this context that you can think of a probability distribution also as a way of just describing your data. But I would say describing and not summarizing, because it's fairly comprehensive. It just does not give you one number or one thing. It gives you the full form and shape of the data, and you can think of it as an exercise also in modeling your data. So you're not just describing it, you're modeling it. So in that context, probability distributions are very important, and we will also see how in various other things, not just describing data, but even in terms of doing more advanced analytics in the machine learning parts and the statistical inference parts, the use of probability distributions is critical. To think of a data set as random numbers that are being generated in accordance to some mathematical function is the whole idea behind the use of probability distributions with respect to data. Okay, to do this, we kind of have to understand some basic concepts, and the first basic one is to understand what random variables are. A random variable is essentially a variable whose value is subject to variations due to randomness, as opposed to variations due to some other phenomena, right? So we're all familiar with the concept of a constant, which just means it's a fixed number, and variable. Here I'm talking about the variable that you probably learned in algebra in high school, non-random variables. And there you learned that a variable is essentially something that can take on many possible numbers or any possible number. But the distinguishing factor between a variable and a random variable is that with a regular variable, once you fix all the externalities, then the variable takes on a specific value. So let me give you an example. So you take something simple like force is equal to mass times acceleration. So force is equal to mass into acceleration, and you might say, yeah, all of these are variables, right? And they are, and that's true. So force can be any possible value. Given what I've just told you, force can take on various numbers as its value with some units. But once you fix mass and you fix acceleration, force will take on a very specific value, as opposed to a random variable where even if you fix all the externalities, the best way to describe the random variable would be to say that it can still take on a set of possible values, and that set could be a very large set. It could be an infinitely large set. But the variable itself can take on many possible values, and each of those values have a specific probability associated with it. And beyond that, you're not going to you cannot reduce the variable beyond that. By definition, even after you've fixed everything around this variable, you still have to describe the variable with a probability state space. So let's the best way to again get this even deeper, to understand this even better, is to talk about some very specific probability distributions, and that's what we're going to do in the next part of this class. But before I proceed, I just wanted to tell you that I'm broadly breaking up the idea of probability distributions into discrete probability distributions and continuous distributions, and that is just to give you some structure. Those words might not make immediate sense to you right away. But what we're going to do right now is to look at discrete probability distributions. You might also notice that I'm using the word probability density functions, and you might not know what that word means yet, but very soon we're going to be talking about that as well. So great. So we're going to look at the most simplest discrete probability distribution, and it's really simple because I think we've all used it in some sense in our daily lives. So we're here. Okay, so let's look at the first example. I'll give these numbers just so that going forward it's clear. Okay, so we're looking at number 1. In number 1, matches the closest with a colloquial use of probability, chance, likelihood, and so on. And we're saying something simple, which is that the probability something happens is X. So you might say the probability that it rains today is 10%. There's a 10% chance it's going to rain today. What goes unsaid is that there is therefore a 90% chance that it does not rain today, and that's what is captured in this graph. So we're more used to saying there's a 30% chance that it's going to rain, there's a 20% chance that there will be an accident, there is a 10% chance that the product that I'm manufacturing is not fit to be shipped. But essentially we're talking about these kind of binary events where one of the possible outcomes is X, and therefore by definition the remaining possible is just 1 minus X. Or if you're thinking of it in terms of percentages, it's 100 minus X. Again, a very simple example of this could also be something like there's a 50% chance that if I toss this coin, I'm going to get a heads. And what goes without saying is therefore that there is a 50% chance that you will not get heads. In this case, that's called tails. So great. So that's one very simple conception of probability, and this is a probability distribution. It's called a Bernoulli distribution. But we can move to multiple outcomes, right? So if you look at number 2, what we have there is what you get when you roll a dice. So you roll a dice, and a dice has 6 faces, and on each face you have dots. So you have, if you roll a dice, you either get a 1 or a 2 or a 3 or a 4 or a 5 or a 6, and the idea is that the probability of each of these is 1/6 if it is a fair dice. And so that's a different kind of a probability distribution. We will soon learn in our next class that that's called a discrete uniform distribution, because they're all the same probability. But the possible outcomes, going back to our definitions, is that so the possible outcomes, possible values are 1, 2, 3, 4, 5, 6. The probability associated with each of those possible values is 1/6. And one thing that you might have noticed by now is if you take all the possible values and you take each probability and you add them all up, you always get 1, right? So in the case of 1, we saw that if the probability of it raining was, let's say, 30%, let's say the probability it rains today is 30%, and the probability it does not rain therefore becomes 70%. You add those two up, you get 100%, or you get 1. Similarly, you have 6 possible outcomes when you roll a dice, and there's a 1/6 chance of each of them happening, and 6 times 1 by 6 is 1. And the intuition for this should also be obvious, that if you roll a dice, or if the day passes, I mean, something has to have happened, right? You have had to have gotten one of those 6 numbers, or it either rained or it did not rain. But as long as you have comprehensively covered the universe of possibilities, then something needs to have definitely happened within that universe. So therefore, that should also be an intuition as to why the probability distribution sum to 1. What we have in number 3 is the idea that, again, it ties to this notion of probability not just being a theoretical exercise, and you might actually have some data, and you might choose to define the probability distribution based off of what you see in the data. So if somebody came to you and said, look, I don't want you to assume that, so I want you to take this coin and I want you to describe this random variable, which is the probability of getting a heads or a tails, and that's the random variable, and I don't want you to assume there's a 50-50 chance. So you might say, fine, I have nothing, I cannot assume anything, and you might toss the coin a few times. So you do a data collection exercise where you toss the coin 30 times, and you notice that you get 14 heads and you get 16 tails. And for whatever reason, if you don't want to assume anything about the distribution, and let's say you also don't want to do any statistical inference, again a topic that we will cover soon, you might just be content in saying, I'm going to describe this random variable with the actual data that I see. So I'm going to actually say that a 14 out of 30, there's a 14 by 30, because you actually got 14 heads when you toss the coin 30 times. So I'm going to actually say 14 by 30 is the probability of getting a heads, and 16 by 30 is the probability of getting a tails. So there's nothing wrong with doing something like that. We would have to see if that actually made sense to do, but nevertheless, if you said, I just want to take data and I want to describe a probability distribution with the data that I see, then you can definitely define a discrete distribution in this way. Now we go on to something that's a little more complicated, which is continuous distributions. In the previous case, in the discrete distributions, and let me erase this, all the ink. So in the discrete distributions, what made it discrete were that the possible outcomes were discrete. So it was either an event or a non-event. So that's discrete. There's no half event, right? So there's no half event, not there. Same way out here, you either get a 1 or a 2 or a 3 or a 4. This set of possibilities, that is your x-axis, essentially has some countable number of possible states. And so you cannot get a 1.5 when you roll a dice. And similarly, you can't get a half head, half tails when you toss a coin. So that's essentially the concept of it being a discrete distribution. And with continuous distributions, however, that's not really true. The idea is that the x-axis out here, so it's the same idea, which is the possible outcomes are on the x-axis, same thing that we saw on discrete, and the probabilities are on the y-axis. Okay, so this is the same core concept of describing a distribution, but here the x-axis is not discrete. So what does that mean? What it means is you take something like the probability of a certain height. A height can be 130 centimeters. So that could be one number out here. But it could also be 130.001 centimeters. It could also be 129.999 centimeters. So there's no inherent discretization. You might turn around and say, look, what if I had a measuring scale that could only measure in 5 centimeter intervals. So the way, or I can only measure up to a centimeter. I can't measure less than a centimeter because the scale that I have does not have more resolution. And that's fine, if your resolution for measurement is still accurate, meaning that anything between 130 and 131 gets called 130 because of the inherent resolution of the scale, that's fine. You can create a discretized version of it. But the idea is there's nothing about height or essentially the measurement of space. There's nothing about height that is inherently discretized, like the measurement of a dice, right, is inherently discretized. You cannot possibly roll the dice and get a 2.5. Whereas if you had a fine enough measure of height, you could get any possible value within a certain range. So you might have the lower end of this being 20 centimeters and the upper end of this being 180 centimeters, but essentially any value between it is possible. And we kind of spoke about the same concept when we spoke about discrete and continuous variables. The same concept of discrete and continuous variables applies to discrete and continuous distributions. Now, again, another important thing to note is, just like in the discrete distributions where we said the sum of all the probabilities for each possibility should add up to 100% or should add up to 1, here you cannot have a countable number of possibilities. So you can't take each possibility, take the probability of that and add it to 1, just because there are infinite number of them. So you basically, what you do is you take the entire interval and sum the probability within that interval, and the best way to do that is to look at this area as a whole, right? So this way, when you look at this area, it's like you're taking all the possibilities within that area and summing all the probabilities for each possibility. And when you do that, you will be getting 1 or 100%. Okay, so now that we understand both continuous and discrete random variables, let's just briefly talk about the use of probability density functions and cumulative density functions. So far, what I have been graphically showing you have all been probability density functions. For each probability density function, there exists a cumulative density function. Okay, and so I'll describe it in the continuous case, and that's the easiest, and I'll separately do that for the discrete. The idea with the PDF is that, like we said, because there are infinite number of possible states, it doesn't really make sense to ask the question, what is the probability at a given point? It turns out that the answer to that question is that the probability of that given point is 0, although there is some there's some height for that given point, because there are infinite such points out here, because there are technically infinite such points. As a result, you can only say what is the probability of a given area. So you can say, I want to look at this area, and you can get the answer to that question. You can get the probability of this given area by just measuring the area under this curve. And that's what I've done with the gray line on this graph as well. But the idea behind PDFs to CDF is that the CDF describes the cumulative probability up to a certain point. So if I were to ask the question, what is the probability within this area, you could answer it for me by looking at the area under the curve. If I asked you the probability density function at this given point, you can use the function to figure out what this value is, but the probability itself is 0. But the cumulative describes the probability from 0, from the lower end of this axis, and that can be 0, or that could be something like minus infinity, or it could be in some other value, the starting point essentially. From that starting point all the way up to the point of interest. So if this is x, right, the PDF describes the height out here for X. The CDF describes, okay, so this is your point X. The PDF describes the height of this curve at X, and which is why this entire curve out here, this curve that's here on the left hand side, is the PDF, whereas the CDF describes the area to the left of this point X, and that area is the CDF. So this graph is nothing but the same as the graph to the left, where at each point X you're looking at what is the area to the left of X on the PDF, and that's what you're plotting here. And that should logically be equal to 1 when you complete. And the reason for it is the following. We've already discussed in the previous section as to how the overall area under this curve, is equal to 1. Correct? We discussed that if you take all the possible states and add the probabilities of all the possible states as to how you're getting you would get a probability of 100% or 1. And so a CDF is nothing but this description of the area to the left of the curve, and when you've reached your entire set of possible heights, or in this particular case heights, but it can be anything else, then the CDF hits at the 1 mark when it ends. So, and it would be helpful for you to know that therefore the easiest way of getting from a PDF to CDF and a CDF to PDF is from a PDF to CDF you would essentially want to integrate. For those of you who used integration in high school or have heard of the term integration, that's that symbol that looks like this, and the idea is that an integration covers this core concept of area under the curve. So if you integrate up to a point X, so let's say just for as an example that this started at 0, but you could change that. It could start at y, it could start at minus infinity, but you essentially, if you integrate the area under this curve, right, to integrate the area under this curve to get the CDF, you would just want to integrate from 0 to x, some f of x, right, and the f of x here is your PDF function, and that will give you the CDF. And the idea of going from CDF to PDF is exactly the opposite, which is to differentiate the CDF, and that will give you the PDF. Okay, so we will conclude this lecture with that note, and starting from the next lecture we will be talking about some actual probability distributions, and we will go through at least the most popular ones in that lecture. Thank you.